So hello everybody, my name is Manfred Schedl. I'm from RoboDrive, which is a brand by TQ Systems. TQ Systems is number 2 in Germany for electronic engineering and manufacturing services. And what I'm talking about is the RoboDrive high-power servo drives in mechatronic applications, as you can see here. And the question is, why producing new motors, as there are so many motor producers already in the world? And where we come from, you see here, it's all started in space. We really did have a robot on site of the space station ISS, which operated for years there, and we had a lot of topics in designing it. What we are looking for is motors for robots. These are machines that do manipulation in space, in industry, or in surgery. So it's not only about driving something, but it's also holding something, exerting torque over time. This is the most impressive demand that we can do on the motors. Of course, as you can see on the pictures, we have these arms. They are produced now in orange by KUKA, for example. We have the hands. They are still under research, not so much of a product. And this is what it's all about. It's the motor housed inside the robotic joint. It's the red part in the middle. And the front side, you see the gear. On the back side, it's the electronics. And this is all covered by a carbon shell. So it's really hard to get off the heat. And any drive problems that you face in the industry in the end is a problem of thermal heat transfer. So what are we doing? We're using electricity to generate motion. And unfortunately, there's also some heat coming out of the system. And this in some terms will limit your application. For years people were thinking of efficiency being the key factor. But imagine a robot that is holding something. It doesn't move at all, so efficiency is purely zero. So obviously efficiency is not the correct number to deal with that, but you need to take care of the overall sum of heat generated in the drive. And there we started thinking how to design an electric motor that is really good in terms of thermal behavior, that has torque and speed available, all that you need for a robotic application. And at that time we named it concurrent engineering. Today concurrent engineering means a different thing, but what we intend to do is taking care of all these topics in the design phase. And how are we doing that? As I mentioned, we start with the customer demand. So we need to know, what is the motor doing? Is it turning all the time like a pump, or does it hold something? And then we have, of course, concepts or constraints like the space that we have or the voltages, and we put this in this magic box called optimization. I show you what's in there. Of course, as any other motor producer, we use an FEM to calculate nonlinear magnetics, but the know-how is here in terms of formulas. These formulas describe motion performance dependent on geometric numbers, and the algorithm finds the right numbers to fulfill these demands. And this is a very unique software that we have. It was all theory, and when they presented me the result, it looks like this. What do you see here? It says, this is the size of a motor, so here are large motors. This is the losses that the motors produce. And it's really simple. A small motor will overheat, producing a lot of losses. A large motor does the deal very easy. And I pointed my thumb here and said, look, if you can build this, it's a motor that has half the weight and half the losses of a commercial prototype. And we checked it and it really works. So that's the result from research that we had there. You see different things. The calculation is correct. It can be measured. And what you also see is that the motors are really good in cogging suppression. So we have 40 dB suppression in all the harmonics. The rotor is really moving very, very smoothly. This is what we provide for the customers. You see that the motors are very linear. This motor is designed for 7 amps of current, and linearity is completely straight. And you run into saturation, you can do this for seconds. So you can really accelerate pretty fast. The motor has superior dynamics with that. And we also supply you with the torque loss due to the core and the torque loss in power for a motor. So you see, you can also go to higher RPM rates with a motor. We provide them in 2 different core classes to make the higher revolutions possible. So much for the technology. So what's it all about? What you can buy here. You see that we built a complete range of motors from very small ones. I've brought one with me. This is a size 25 motor. In this longer version, it's capable of about 100 watts. The standard version is about 60 watts of shaft power, which can be done here. Up to 2 kilogram motor sets, which are capable of 40 Newton meters in peak torque. Here you see our small baby in a cross section. The technology we use is an orthocyclic winding, so you really have a very dense copper fill factor. Cocking suppression is done by geometric design. It's not done by skewing rotor or stator. And we have a vacuum casting that really yields excellent thermal behavior. So we definitely know how to bring out the heat of the motor. Some technical data, I skip that, you find it in the website, it's all available. And come to the customer applications that we can show. It's not so many I can show because these products are directly designed into customer machines. It's their proprietary knowledge, of course, so just a few of them to give. These are the fields that we are mainly in. This is something also from my history I'm really proud of. It's a piece of space hardware, a 2-axis robot. 1 axis, 2 axis, and you can see that it's morning gym, it's pulling the string here. It's the only piece of space hardware that has been 6 years up in space, outside the space station, and we brought it back in a Russian cosmonaut in a Soyuz capsule, back on ground for inspection. I was really surprised how that looks like. It looks like it has been on a tank ship on sea. All the aluminum is really corroded by this atomic oxygen in the atmosphere and radiation. That's impressive to get it back. But when you open it, it's as new. It's all under vacuum, no dust, no housewife cleaning necessary. More commercial things. These motors are, for example, able to fulfill full speed and power density also at automotive power supply. So when you have only 14 volts or 12 volts of battery voltage available, you can do very, very dynamic applications. This is an electrically actuated automotive brake under full testing. This is an example for a tool changer in a milling machine. Usually they have a hydraulic cylinder placed right upon the milling spindle, and the hydraulic cylinder compresses the spring to eject the tool of the machine, and then the next tool goes in. And since this is the only hydraulic equipment still used in milling machines, they try to replace it by electric motors. And you can see what happens here by this shoulder bearing. There's a pretty much thrust coming out of that, and we are able to do that with the same performance as an hydraulic cylinder can do. So power density is really superior. Here you see the 85 motor. Nobody tells you that 50% of the power goes to the bearing and the other 50% does the pushing stroke. On the other hand, leaving the power, going to precision. We are building gimbals, for example, for cameras and other applications with very high resolution. Because this motor is optimized in its volume, it's very easy to switch the torque from one side to the other. You need to change the magnetization in the iron. So the torque bandwidth in the motor is really superior. And that makes it possible, for example, for a police helicopter camera. Not everybody likes that. It has infrared sight, laser radar, and picturing unit camera, and the pilot sees on a LCD screen how fast you're driving. It just pushes the knob with a picture. We do the control up to 1 increment in flight condition. And this can even be much better. This is a solution for data transfer from an airplane to on ground. So the ground station is this. It's usually located on the roof of an embassy. And what you want to do is you want to bring down the data, picture data for example, from an airplane to ground with a connection that cannot be interfered in any means. We do this by a laser beam that comes from the airplane going to the ground station, which is fairly simple. But when you cross over with a jet airplane or a military airplane over the embassy, you need to be pretty fast too, not to lose track of the ground station. We are using here encoders with up to 50 million increments per revolution, and in flight over we have an accuracy of about plus minus 13 increments. So really accurate pointing even from fast flying objects. This is one of the strongest actuators that we have built. It's an 85 motor here too, combined with a two-stage harmonic drive gear. This has 30,000 Newton meters of torque. It's used to open the door in Freightliners. And I was surprised by the reliability figures that we were facing. They told us the failure rate should not be larger than 10 to the power of -9. And I said, oops, that's really difficult. And I said, yes, and we will test it over lifetime. So they built a huge test check with 3,000 Newton meters of load and put the actuator in. And we really succeeded in the test. I'm happy about that. Still some time left, I think. Okay, this is another example for more precision pointing with a larger motor. This is a size 115 motor. So the core set with iron and rotor has a weight of about 1 kilogram. And what this is doing, this is a spectrometer which is flying on that airplane. It's in the belly pod, side looking. And the job is to make a spectroscopy of the atmosphere. So the measurement point needs to be dragged during the measurement when the spectrum is acquired. And after that, the whole spectrometer needs to be repositioned to the next measurement point during the airplane is flying. The cycle of measurements is 2 seconds, and we have only 0.7 seconds to reorient 45 kilograms of spectrometer within 12 to 16 degrees. So it's really a fast motion, and you hear it in the cockpit of the airplane when this thing starts bumping around in the belly pod. The pilots don't feel so comfortable about that. But it's really working, and it also has a very high resolution encoder from Renishaw here on that side. This is a nice little robot, very useful. We supply the motors for the chain drives here, for the arm. And there is a camera and a 2-finger gripper on top. It's used for bomb liquidation. So this device is capable of going over the runway of an airport at around 40 kilometers per hour. Then it slows down, entering up the slope here. And it can raise its head to look in the overhead compartments. And it can make itself very small to look underneath the seat. Usually it has a tool set here behind, which consists of an X-ray and a water pump gun. And with the X-ray it tries to find the ignition circuitry of a bomb device, and with the water pump gun it just shoots out the igniter of the explosive material. And it's all battery driven, so in the trunk here you have a battery compartment, and they really rely on that the system does its service all over the battery charge. They use even the latest second to do their job. Another big market coming up are medical devices, actuated medical devices. I have an example in robotics in here, but we are also doing endoscopic devices or optical devices, scanning devices for medical purposes. What you see here is that such a medical robot is smaller than an industrial robot. This robot has about 1 meter and 30 in length, and this is even smaller, because the space at a surgeon's table is really limited. The surgeon and all the people working around, they need to act directly on the patient. They need to be very fast if something happens. So what they did is they built a robot that looks like a human arm. So it has a shoulder, an elbow, and a hand, such that the surgeon knows when he wants to put the robot away, he just touches it and moves it away. He can do that very well with something that is like a human arm, and it's a bit fussed up with all these axes in an industrial robot. It's a 7-axis robot, so you know it's redundant. 7 axis means you can fix your hand as any human can do, and you can still move away the elbow out of the action, which is very necessary to keep clear the area in front of the patient here. And this is the future of medical robotics that we see. There are already medical robots in operation from Intuitive Surgical, large, huge robots. These robots are fairly small, and the reason why they are so small, they have also this 7-axis design. They have 3 axes here in the tool. What we want to do here is operating on a beating heart. If you get a bypass surgery, most of the painful things is the opening. Doing the surgery on the bypass is not so hard to do. It's a standard operation that you do. And this is done here by a camera that's inserted into the body. The camera sees the beating motion of the heart and the breath that the human takes. And so the motion of the other robots is synchronized to the beating motion. And then the surgeon has a screen, and as you have all in your mobiles, you have this shaking elimination on the screen. So the surgeon sees a virtually standstill heart. And therefore you need a robot that is capable of doing a heart's motion and overlaying the surgical motion for the needle. And this is done here in a control technique. Of course, we do a lot of other projects. These are the funny ones that we are doing. A few of our 10,000 motors we build a year go into space. This is, for example, for Mascot, which is a mission to a comet. We have also in some rovers for camera alignment, for wheel drives, for solar panel orientation, especially the smaller motors. They are used in space-qualified versions. In any European humanoid project from any company, these motors are used, especially also in exoskeletons. Upcoming market for rehabilitation, making people move again. They need wearable motors, so the motor doesn't need to be too heavy because they have it on their bones, for example, directly attached to the knee for the motion. They cannot use an industrial motor that sticks out 10 centimeters of your knee. It's not so good. And the other thing is camera systems and cinema systems. We are all used now to high definition technology. It's not so easy to do that in very good resolution and to synchronize this blue screen motion of the actors with very often calculated by computer rendered schemes. And this is done by camera robots that guide the vision point directly in the studios. I've talked now a lot about special motors, integrated motors in customers' applications, and we found out that it's also useful to have motors that we can sell off the shelf, just for a customer who needs a drive. So what we did is we built some devices that we give now in our product range for selling directly. This is the strongest one that we have. It's an Elmo Twitter, which is a very, very small inverter. And we use 3 of them. You see them located here in the corners. They have these cooling covers here. Then we have a massive metal body, which is also capable of water cooling. We have inlet and outlet here, and a large bearing. And we have this drive. It's an 115 drive, which you have seen on the spectrometer inside. And this is capable of 5 kilowatts of peak power. Imagine that to be a round table. Well, you can buy any round table in industry already. But imagine you have a process that is really fast. So you need fast acceleration, short settling time, accurate positioning. So you need both. You need the high torque for acceleration. You need the high speed during the motion. This one can accelerate up to 2000 RPM. And it really does that within half a revolution. And it can have a pretty heavy load on that. So we supply both the torque and the speed. And we do this in rather fast cycling. And we use these triple inverters on redundant windings, so each of them just powers part of the windings just to get the power into the motor, which makes it very effective. And the other motors we have now are framed motors, so it's not only rotor stator kits for integration, but you can buy hollow shaft systems, which include sensors and brakes. We also have the sensors and the brakes available as components, for example, if you need it. And we provide geared solutions, planetary gears. I've brought one sample with me. So these motors in the size are able to really bring all the torque that the planetary gear is capable of doing to that. We're combining them with different types of gears. This is a Maxon gear, but we use Neugat, for example. Neugat has a distinctive website where you can choose your gear, any gear you want, or Güssing gears for higher precision. And we also go to harmonic drive or cycloidal gears. That's where we come from in robotics, so we have a lot of experience with these ones. Yeah, so much from my side about RoboDrive and the products. We are not so known on the Scandinavian market, so we have a partner here, which is located in Stockholm. It's Compotech. We are here on the fair. with our friends. So just step by and visit us if you have any questions. You're welcome. Thank you very much.